All right, chemistry students. Earlier we saw in the video that we could use a simple recipe type analogy to think about how reactions would occur and whether there be a limiting reactant. Just remind ourselves that the limiting reactant is the reactant. And that's important. It's the reactant that we run out of first. Just want to remind you that whenever we have a reaction, it's always reactants going into products. They turn into products. The stuff we put in the container initially are reactants. So if you're giving me a limiting reactant, okay, you need to actually make sure it's a reactant and not a product that you're telling me about. All right. First, let's just look at a simple example to kind of get a feeling for how this all fits together. And we've done this picture view before, but this will really help us clarify. So imagine we have the reaction of 2 hydrogens and 1 oxygen making for us 2 waters. We could start with a container that might have, let's say as is pictured here, 6 of each water, or 6 of oxygens and 6 hydrogens each. So if we were going to use this particular example as a reaction, we could then start crossing off to see how we're going to make these things. Remember, we always have to look at the ratio of how they're made, 2 to 1 in this particular case. So let's start crossing these off. We need 2 hydrogens and an oxygen, and that will make for us how many waters? 2. We then can do the same thing again, 2 hydrogens and an oxygen. We can do it one more time. Finally, 2 hydrogens and an oxygen. And what we've seen is we've now used up all of our hydrogens, so our limiting reactant is equal to H2 in this particular case. So the important part about that is we can now see a couple things. First, we have remaining 3 oxygens. And so that's going to be over here in our container. 3 O2s will be over here. But the question is, what else will be in that container? Well, what we know is we know we've used, wrong one. We know that we've used hydrogen up. So knowing how much hydrogen we've used, we can then figure out how much water we'll make. All right? So what we know is this. If we're trying to find the number of moles of water that we've made, we know that we've used up 6 moles of H2. And according to the reaction, for every 2 moles of H2, we're going to make 2 moles of water. 2 moles of H2 will give us 2 moles of water. We got this from the balanced reaction. Those cancel out, and that means we can make 6 moles of H2O. 6 moles of H2O. Great. You know, we should be able to double check to make sure this is right, because if you think about it, we also know that we used 3 moles of oxygen. So according to this, we should be able to find the same information if we looked at it from the point of view of oxygen. So the number of moles of water we can make from 3 moles of oxygen. Notice it's not all 6 moles of oxygen because there's still 3 left over right here. We've only used 3. This 3 right here have been used. So 3 moles of oxygen. According to this, for every 1 mole of O2, we can make 2 moles of H2O. Where do I get this from right here? This little ratio? I get it from the periodic table, and I'm going to do this in green. For every 1 mole of oxygen, I can make 2 moles of water. Knowing that, if I do this math, once again, I get 6 moles of H2O. So both of these, either way we look at it, give us our answer that we want, which is how much water can we make. So this number of water molecules made would be our theoretical yield. It's the most we can make. It's the maximum yield that we can make of water from this particular setup of reactants, initial conditions. All right, we're going to do some more calculations with this in the next video with written down type reactions instead of picture view.